We're going to look at conditions for inference on the mean. And now, we talked about inference in the past. It's that ability to predict something about the entire population from just a small scattered SRS, or a small sample of data. So we're only going to collect some data, and we're going to make a prediction about the whole population. So in order to do that, to do confidence intervals, or what we'll talk about later, hypothesis tests, what we need to do is have a couple conditions met. Looking at how we used to do it for proportions, the two things that we needed was good data and a sampling distribution that was normal. The good data came from taking an SRS, or something equivalent, and it also came from having low undercoverage, low non-response, and very few other biases. So good data came from designing a good sampling of the population. The second thing was more technical in nature. We were looking for a distribution that would end up looking like a normal curve. And when we did things with proportions, we were using the binomial distribution as our base. And if we had at least 10 successes and 10 failures in a population that was at least 10 times the initial sample size, we would end up with a binomial distribution that ended up being almost a perfect normal curve. So if we had not met these conditions, then we might have ended up with something that looked more skewed or didn't make a very nice normal curve, and that would give us some problems when we were doing our inference. So we had to make sure these minimum conditions were met. Now when we're dealing with the mean, when we're using x bar and we're predicting mu, the population mean, we still have those same two conditions. We still need good data, and we get good data exactly as we did before, using the right technique and trying to minimize our other biases. However, we also want to make sure that our sampling distribution is normal, and in order to do that, we rely on the central limit theorem. If we start with a distribution that's normal, it doesn't matter how big our sample size is. So if we have, let's say we're looking at things like heights that are normally distributed in the population, we could have a sample size of 1, and that would be okay. However, if we don't, if we have, like most distributions, some skew or some crazy shapes going on, then we would need to make sure that our sample size was large enough. And referencing what we talked about before, if you have a very, very crazy distribution, you're going to need a sample size of at least 40. Whereas if your distribution is somewhat normal with a little skew, maybe 15 is fine. And if it's perfectly normal, again, 1 would be okay. So the size of the sample you need depends on how crazy that initial distribution is that you're looking at. So let's take a look at a quick example. We have an SRS of 25 runners, and they had a mean time of 19.65 minutes in the race, and a standard deviation of 1.36 minutes. So we took an SRS of these 25 runners, and we found their average time and the standard deviation of their times. First question is, will our sampling distribution follow the normal curve? In order to figure this out, because 25 is still kind of in the borderline area for a sample size, what would we expect from a bunch of runners? If it were me, I would probably expect to have a somewhat unimodal, maybe slightly skewed distribution, where on the fast end, there's some people that are really fast, and then there's kind of the typical runner, and then you would have potentially some very slow people, so it might skew off to the right a little bit. Now, if we start out with the base distribution, it looks something like this. 25 people is going to be absolutely enough to make sure it follows the normal curve. So, and it's also going to shrink that standard deviation. So our sampling distribution is going to look something more like this compared to that original curve. Probably even tighter than that. Next question, what is the best guess of the mean of the distribution? Well, we don't know the population mean. We don't have data on the whole population, but our best guess is always going to be the average that we're given from our data. So this value right here, we call this x bar. That's the average from our sample. That's going to be our best guess of the mean. We always use x bar to guess what mu is if we only get one guess. So So we'd say 19.65. And then the next part, it says, what is the standard deviation of the sampling distribution? To figure that out, we're going to use our handy little formula that we found with the central limit theorem. And we know that our sample size, n, is 25 up here. So we're going to go ahead and circle that. We also know the standard deviation of the sample. So our sample standard deviation is equal to 1.36. So I'll throw a box around that. So now we know all our values that we care about. And this formula says we take that standard deviation and divide it by the square root of n. So I'm going to take that 1.36 and I'm going to divide it by the square root of 25. And if we pull out our calculator real quick, 1.36 divided by square root of 25, or divided by 5, that's going to be 0.272. So what we just found right here, the standard deviation of the sampling distribution is going to be 0.272. And if you want to carefully label that so that you can keep track of it later, we're going to call that S X bar. And the reason we do that is that way it's just a simple little way with our notation to keep track of which standard deviation belongs to the original data and which one belongs to the updated one based on the sampling distribution. And that's why we say the standard deviation of the averages or of the X bars.